Hi, this is Mark Leach with Simpson Math, and today we're talking about probability. In this example, we'll cover sample space, the OR probability, and a classic example of independence. What you'll need to do in a minute is to pause the video, read the question in its entirety, including all four parts, grab a piece of scratch paper, and try this out on your own. Once you've finished the question to the best of your ability, go ahead and press play, and I'll be there to show you solutions and some tips and tricks along the way. So go ahead, pause the video, and try this out on your own. All right, welcome back. Let's take a look at part A. So in part A, you are asked to complete a table to help you figure out the sample space. Well, let's first take a look at it. So along this diagonal, we see this is the times when the teacher role and your role actually is the same. And then above it, this is when the teacher role is larger than your role. And below that line is when your role is actually better than the teacher role. What I highlighted in purple, I'll fill in with dashes. Above that, what I highlighted in blue will fill in with T's, and the rest in green will fill in with Y's. So let me erase that and fill this in. All right, so there's our sample space. Next, we're asked to find out the probability of A, which is the probability that your teacher wins. With this sample space, every one of those letters or dashes are an equally likely event. So in order to figure out the probability, we just have to count up our number of successes and divide it by the total number of possible outcomes. So for probability of A, all we need to do is to count up the total number of T's and then divide it by the total number of possible outcomes. But if you count up the total number of T's, we see that there are 27. And to find the total possible number of outcomes, we notice that this is a 6 by 8 rectangle, so all we have to do is just multiply 6 times 8 and get 48. So let's plug in our possible number of T's, which is 27, and divide it by our 48, and then divide it in a calculator and get 0.5625. So the probability of A is 0.5625. For part C, we're tasked to find the probability of A or B, where A, again, is the event that your teacher wins, and B is, this time you get a 3 on your roll. Recall that U symbol or union is OR. So just a reminder about OR. As long as there is one success, including both successes, the OR is satisfied. So if just A is a success, or if just B is a success, or even if A and B are successes, all three of those circumstances satisfy the OR condition. Now, in full disclosure, this question could be worked without the two-way table, but I teach my students to answer these OR questions using a two-way table, so I want to show that first. In addition, for part D, I find it easiest to be using a two-way table to answer the independence question, so let's go ahead and fill out a two-way table. We can put the information from the previous part, so there are 27 times the teacher wins out of a total of 48. So we can just subtract and get that there are 21 times the teacher does not win. Notice A complement, or not A, is the times when the teacher loses and also when you and the teacher tie. Next, we can count up the number of times you get a 3 on your roll, and we see that that's 8 times, so we just have to subtract, and we get 40 times that you do not get a 3 on your roll. In order to be able to determine the other 4 squares, we just need one more of these values. So looking at our sample space, we see that there are 5 times when you roll a 3, but the teacher wins. So we can put a 5 in that upper left-hand cell. So at this point, through just addition or subtraction, we can find the remaining cells. So if we do 8 minus 5, we get 3. Then 27 minus 5, we get 22. And then for this last cell, I like to check it in both directions just to make sure that I didn't make any arithmetic errors. So 40 minus 22, or 21 minus 3, is just 18. So now let's answer our OR question, the probability of A or B. So I go through my 4 main cells, not counting the total cells, and I just ask myself, is this situation A or B? If it is, it goes into my numerator. So in the top left corner, is that 5 A or B? Yep, it actually is A and B, and as I discussed earlier, that is a part of OR. Next, that 3, That 3 is A or B because it is the B, even though it's not A. The 22 in the bottom left-hand corner is also part of the OR because it's when A is a success. But that 18, it's when A is not a success, nor is B, so it is not a part of our OR statement. So for our numerator, I need to add up the 5, the 3, and the 22 because that is my total number of successes, and then just divide by our total number of possibilities, which is 48. So we end up with 30 over 48, or 0.625. Some of you might be familiar with a formula to determine the OR probability. I cover that in another one of my probability videos. The link to that video is linked in the description below. Like I said earlier, you actually could have pretty easily answered this question without the two-way table. Remember, there are 27 times when the teacher wins, and here are the times when you roll a 3. So we just need to add up these 3 additional times when you roll a 3, but it wasn't being already counted when the teacher won. So that's 27 plus 3, or then 30 over our 48. So that's how we could have actually pretty quickly have gotten to the 30 over 48, or 0.625. Lastly, let's talk about independence. So in order to determine if two variables are independent, we need to compare two probabilities. We need to compare the probability of A to the probability of A given B. Notice the comparison symbol there. It's an equal with a question mark over it. Sometimes I'll just call it equal question mark. What that is that's begging the question, is the probability of A equal to the probability of A given B? So I'm not saying they're equal. We're actually saying we don't know. We're going to be testing if these two things are equal to each other. Later at the end, you should end up with either a definitive equal sign or a not equal sign, or in some cases, maybe an approximately equal to. If you're a memorizer, you can just memorize this fact. You got to determine if the probability of A equals the probability of A given B. But I'm not very good at memorization, so I like to think of a quick little practical story. I like to think about how I behave or act or speak if I'm just by myself. And then if I compare that to how I behave or act or think, given that I'm with somebody else, if that changes when I'm with this other person, then clearly there's some sort of relationship between how I act or speak or think when I'm with this other person. But if how I act or think or speak doesn't change given I'm with this other person, then I'm independent. So if you look at the formula, think of the probability of A. Whatever it says, I'm going to be testing it with whatever it says given that it is with B. So if those two probabilities match, then A basically doesn't care what B does or that B has already happened. So then A and B are independent. But if those probabilities don't equal, then there's some sort of relationship between A and B. So we need to find the probability of A and the probability of A given B. I teach my students to circle or draw an oval around the probability of A and then around the probability of A given B. When they do this, these ovals better be parallel to each other. They do not need to intersect in any way. They need to be parallel, and one of them usually should be a marginal probability. So let's find the probability of A. So the probability of A is that oval right there, and so it ends up being the 27 over the 48. So my number of successes, which is 27, over my total possibilities, which is 48. If you recall, we found this back in part B, so 27 to 48. And we're going to compare that to the probability of A given B. Notice I drew that oval parallel to the bottom oval. If they intersect in any way, your relationships are not correct. So I'm going to be comparing 27 over 48 to 5 over 8 because there are 5 times that the teacher wins out of the times when you roll a 3. So A given B is 5 over 8. Now, I left the equal question mark with these fractions because if somebody told me to quickly determine if these two fractions equal, I knew that they're close. They're both bigger than a half, so I'm not real sure. So it's easiest to make this determination when they're decimals. So 27 over 48 is 0.5625, and 5/8 is 0.625, and those two decimals do not equal each other. Now, you might be thinking to yourself, but I remember a time when my teacher told me that if the numbers were close, that it would be okay. And that's right, but I have this to say about that. In this situation, these probabilities are theoretical probabilities rather than just observed or empirical probabilities or just a random sample. If I would have gone out and sampled 48 people and came back with this results, then it might be plausible that we wouldn't be able to actually definitively say that these two things actually are independent. So in this circumstance, because these are theoretical probabilities, I can firmly say that these don't equal each other. On top of that, if 27 over 48 was actually 30 over 48, then these fractions would equal. So let's answer this question. Are the events A and B independent? Whenever you are asked a yes or no question, make sure the first words, the first way that you actually answer the question is with that definitive yes or no. So are the events of A and B independent? No. What else should we say to support this? We say that since the probabilities don't equal, A and B are not independent. So on a test, it's important that you make sure you start with a clear relationship, show your work, make a determination about whether they do or do not equal, and then make sure to answer the question with either a yes or a no. Now, you could do this the other way. You could compare the probability of B to the probability of B given A. You would end up with this vertical oval, 8 over 48, and we would be comparing it to 5 over 27. So 8 over 48 does equal 5 over 27, and it ends up, it's 0.16 repeating to 0.185 repeating, and those do not equal for those same reasons, because again, these are theoretical probabilities. Though they are close, there's just a little bit of a dependency there. So again, we say no, the probabilities don't equal, so A and B are not independent. So there you have it. I hope this example helps you understand probability a little bit better, especially when it comes to finding the sample space, determining the value of the OR probability, and especially independence. Thanks for watching, and see you next time.